Okay, let us start out today's seminar. And today's speaker is Victor Janusz, a master student from Moscow State University, who will give a talk about Hamiltonian Monte Carlo sampling in the space of orthogonal matrices, which play a very important role when we deal with very deep neural networks.
Thank you for the introduction. So, before we start, I want to point out that before we get to the main goal, we'll need to cover a few topics which are quite important on their own. So I hope that even if you don't understand everything from my talk, you will learn something useful. Okay, so let's start with a motivational example. There is a model called unitary recurrent neural network, URNN, and it's the same, it's like the usual RNN, except that we make hidden-to-hidden matrix unitary. And why would we do that? Because it solves vanishing or exploding gradients problem, and the network can't forget anything, and it can use all the sequence and put it in the memory. So this model beats LSTM on sequence copy task and pixel by pixel near specification, because we have very long sequences, and unitary RNN can remember all the sequences. So for simplicity, we can replace the unitarity for orthogonality constraint. So why does it solve vanishing or exploding gradients? I won't go into much details, but here is a sketch of the proof. So by chain rule, we can rewrite the gradient of our boss with respect to some hidden state. Then we can compute the norm, and actually we can bound it. And the norm, this bound, depends on the norm of matrix D, which is a Jacobian of nonlinearity transform, and it depends on W. If the W is orthogonal or unitary, it doesn't change the norm of Jacobian, and so we can just write it using the norms of matrices D. And we can influence norm of D by changing the nonlinearity. So for example, if we take value, we will have, if at least some of the neurons are still active, we will have this norm equal to 1, and so our gradients will not vanish. And also they will not explode because our norm is bounded. Okay, and why do we even care about orthogonal matrices? It's not only about the RNNs. For example, for GANs, orthogonal regularization helps to make the learning more stable. For usual networks, we can provide additional regularization because the capacity of orthogonal weight matrices is strictly smaller than for unconstrained matrices. Also, in the experiments we see that this makes learning faster. And we can also use orthogonal matrices to reparameterize other kinds of parameters. For example, we can reparameterize low-rank matrices using SVD. And the most interesting example is tensors in tensor train format. And there are also others parameters which we can reparameterize. So how would you apply Bayesian inference to the URNN? There are two ways. One way is to use variational inference. However, with orthogonal matrices, it results in either very complicated inference with semi-implicit distributions, or we can use only very simple distributions which induce high bias, and our posterior is not very useful. Instead, we can use Markov chain Monte Carlo. It's a bit slower, but it's unbiased, and we can construct true Bayesian ensemble using samples from Markov chain Monte Carlo, not like from Markov chain. So we choose MCMC. Let's state the problem formally. We want to sample from some distribution which is known only up to the normalizing constant. And this distribution is usually the posterior distribution of some probabilistic model. And we need samples from the posterior to compute predictive distribution to do Bayesian inference. For example, we can estimate the variance of our predictions. And now I will describe how MCMC works, and later how Hamiltonian Monte Carlo works. It's the most popular HMC algorithm. Okay, so Markov chain Monte Carlo algorithms consist of proposal distribution, Q, which allows us to get new samples given the old ones. But as the proposal can be arbitrary, we cannot guarantee that all the samples will be from the correct distribution. And so we need to apply Anthropoulos-Hastings correction, which rejects or accepts sample based on some probability. And you see that proposal should be efficient enough so that we will not reject too many samples, because if all we do is rejecting samples, we don't get any new samples. Okay. So in Hamiltonian Monte Carlo, we work with not only our parameters theta, but also we augment parameter space with new auxiliary variables R. Theta and R represent some point in the phase, so-called phase space, where thetas are the coordinates and of some points, and R are their velocities. Joint distribution is usually written in terms of Hamiltonian, and maybe you know from physics that Hamiltonian is sort of energy of the mechanical system. Most often we choose condition, and also we have joint distribution on theta and R, and we can see that there is a conditional distribution of R given theta. Usually we take just standard normal, or maybe we can precondition it. However, the Hamiltonian most often looks like this. Okay.
So the joint distribution is factorized, right?
Yeah. Okay. So the important point of why HMC works is because we can quickly explore the distribution by following the Hamiltonian dynamics. And why is that? Because Hamiltonian equations conserve energy. And so the Hamiltonian is constant if we integrate the Hamiltonian equations. And that's why if we start from some point in space where Hamiltonian is low enough so that the probability is high enough, we will stay in that region and quickly explore it. So, how to propose samples We have some theta O, maybe it's the initial point of our Markov chain, and we sample some R from the conditional distribution. Then we can...
Is it true that according to your choice of conditional distribution, R O doesn't really depend on theta O?
Yes.
No dependence?
Yes, but there can be. Okay, so we integrate Hamiltonian equations for some time, and we get some new theta and R. And then we can just throw off R, and theta nu will be a sample from our original distribution P over theta.
What are Hamiltonian equations? How do you integrate them?
Well, it's the interesting question. You'll see it in the next slide. So now, for now, we can assume that we can integrate them analytically. And if we can do that, acceptance probability is equal to 1, and it's very nice because we don't even need to do rejection. And the acceptance probability looks like this because the proposal distribution is actually symmetric. But the point is we can't integrate them analytically almost always. There are some cases, but not with, for example, neural networks. And so the only choice we have is to integrate numerically. The most popular way to integrate Hamiltonian equations is to run leapfrog integration. It looks like this. It's just 3 equations, one half step by r, then one full step by theta, and then another half step by r. And as we introduce some discretization error, we need Metropolis-Hastings correction, because it's no longer true that Hamiltonian is the same. It can be slightly different, and so we need correction. But why do we even choose leapfrog? Why is it good? It's quite intuitive that integration scheme, like the solution given by the integration scheme, should inherit some properties of the true solutions. For true solutions, we have 2 important properties. One of them is reversibility. It means that if we go from some point theta nu in the reverse direction, and for the same time, we get to the same point which we started from, and our velocity will be reversed. The second important property is energy conservation. And it's quite easy to see that leapfrog is reversible, because if you change r to minus r, you just write the equations in the reverse way.
Probably you mean epsilon to minus epsilon.
It's the same, actually.
Okay, and what about, say, Euler's scheme? Is it reversible or not?
Which scheme?
Euler's.
Euler's. Yes, I think it's reversible.
Mm-hmm.
There exist reversible versions of Euler's schemes. The initial is not, but they exist.
Yeah.
And what is the difference between reversible and the initial versions?
It's sort of, you use like in the one scheme which is not reversible, you use velocity at the current point, and in the reversible version you use velocity from the next point.
It's like implicit.
Yeah.
So this is implicit model.
Yeah.
Implicit numerical. Mm-hmm.
Okay, so it's reversible. And what about energy conservation? Why do we even want energy conservation? Because our acceptance probability depends on how far from the true Hamiltonian, how far we diverge from the true Hamiltonian. So there is a sufficient condition for approximate energy conservation. It's called symplecticity. It's some quite technical condition. You can test the leapfrog for, you can prove it by the definition that leapfrog is symplectic. And so it conserves energy quite approximately, but the error is not high, and so the rejection rate will also be quite small.
What is the exact definition of symplecticity?
Is
it this one?
Yeah.
you consider the Jacobian, and this equation should be satisfied for Jacobian, for one step of your integration scheme.
And this symplecticity guarantees that the energy is conserved, right?
Yeah, sort of. If you fix the length of like the number of integration steps, then the error is bounded.
So it's not zero but bounded.
Yeah.
Okay.
And like the bigger the epsilon you take, the more the error also is bigger.
The larger is your deviation.
Yeah. So let's look at the leapfrog again. Now assume that we have some constraints on theta, which is the case for orthogonal matrices. And why? What do you think? Which equations fail? At least one of the three equations fails. Yeah, it's actually the second one. And why is that? Because assume that theta n is, for example, orthogonal matrix. Then we add epsilon r, and r is quite arbitrary matrix, and the result of this addition won't usually be orthogonal matrix. And so we violate our constraints. And why does it happen? Because HMC doesn't really know about any constraints, so it cannot handle them.
Well, here gradient is gradient in the space of all matrices, not a projection on the manifold. Or
yeah, and even if you project, you won't get correct scheme.
Some orthogonal matrices is not orthogonal.
Yeah. And so we need some concepts from Riemannian geometry to fix these equations. And it's quite beautiful and not too hard to understand them, I think. So let's dive in. The central object in Riemannian geometry is the so-called manifold. It's, informally speaking, it's a set which looks like Euclidean space around every point. So consider, for example, ellipse. At every point, like imagine that you stand on the ellipse and you can look forward and backward, and the space looks like straight line. So, like ellipse really looks like straight line near every point. If you
mean two-dimensional? In two-dimensional space?
In 2 dimensions, yeah. Also, ellipse has two parameterizations. They are quite different. One parameterization uses t, some variable t, from 0 to 2 pi. And you can, for every point there is t, which corresponds to the point. And notice that we have, like, one ellipse is one-dimensional manifold, because you can just, make a straight line from it. And we have one coordinate. But there is another parameterization. It's the xy parameterization, and xy belong to the plane. But in order to parameterize one-dimensional manifold, we must have constraints on the xy. And we can say that ellipse is embedded into the plane. And so the first parameterization is an example of intrinsic coordinates. We have some coordinates which are unconstrained, and the number of coordinates is the same as the dimensionality of the manifold. The second parameterization is the example of extrinsic coordinates. You can embed the manifold into some space, which is higher dimensional, but you will have constraints on your coordinates. So, yeah, this slide is just what I said. The important thing is that for the intrinsic coordinates, conventional HMC can be used because there are no constraints and the leapfrog works like everywhere else. For the extrinsic coordinates, you have constraints, and so conventional HMC fails. Orthogonal matrices are usually represented in extrinsic coordinates, and it's quite hard to work in intrinsic coordinates because you cannot even write with some convenient parameterization of rectangular orthogonal matrices.
Can you please explain why HMC will fail if we do just projection like we do for Riemannian optimization?
Well, you'll see a bit later, but basically the scheme will not be reversible and symplectic. Okay.
What is G of T?
G, it's 5. No?
G of t on the first equation.
Oh, G of T. It's something called Riemannian tensor. It defines scalar product at every point in the manifold, and it can be used to define like a distance on the manifold.
So this is an analog of Gram matrix.
So,
Yeah.
why does it depend on 1 point but not 2 points? Yeah.
No, we stand in the point at the point T. There are two vectors from this point, u and v, and we want to compute scalar product, and it depends on which point T you.
Okay, I see.
Okay, so the next concept is the tangent space. For extrinsic coordinates, it's easy to imagine tangent space. For example, here you can see ellipse, and at every point you can draw a tangent, and this tangent is a linear space, and this is the tangent space. And for smooth manifold, there is a tangent space at every point.
Wait for a moment, but you've told that a manifold is something which behaves locally like Euclidean space.
Yeah.
Does it mean that this already should be smooth manifold? If the manifold is not smooth at some point, then at this point, at the locality, at the proximity of this point, the manifold will not behave like a Euclidean space.
I think maybe no. There may be some
There are
complex
different kinds of
example.
manifolds you can restrict to continuous matrix, and there are continuous manifolds, and behaves like Rn means that there is a continuous projection from the adjacency of this point and Rn.
So it can be continuous but not differentiable.
Yes, but then can we say that it behaves like a Euclidean space at the proximity of this point?
Yes,
Yeah.
it means on how you define the
This
shape of behaves like.
Okay.
Okay, if there are no questions, let's continue. It's quite interesting to define what is gradient on the manifold. It's called the Riemannian gradient. And Riemannian gradient, what is the usual gradient? It's some direction along which the function grows the fastest. The Riemannian gradient is the tangent vector with the same property. So, but how to compute it? You can write Taylor expansion, and you can, on the manifold, you can move only along the tangent vectors, so you should restrict dx to the tangent space. And so you can decompose gradient into parallel, into tangent and normal part, and one of the inner products vanishes, so you have only the tangent part. And so you can compute the Riemannian gradient as the projection of the usual gradient onto the tangent space. Is it clear?
But this is not the projection of the gradient on the manifold itself.
No. Okay, so now we can return to the HMC. And now we can think what is the domain of theta and r. As we know, theta lies on the constraints, and constraints define some manifold. Like, let's assume the constraints are smooth, so the manifold is smooth also. And r represents the velocity, and velocity, as we know, should lie in the tangent space. So now we can try to fix the leapfrog equations with that knowledge. So take a look at the first equation. We want Rn to lie in the tangent space at point theta n. And in the original leapfrog, we added gradient. Here, it makes sense to use Riemannian gradient, and it will lie into the same tangent space as Rn, and so we can add them, and this operation will make sense. So first we replace usual gradient with Riemannian gradient. Now,
so that we can guarantee that Rn plus 1/2 lies in the same tangent space at the point
yeah,
theta.
and we can't add vectors from different tangent spaces.
Right, but we're adding vector from the same tangent space.
Yeah.
Why is it written that it doesn't belong to tangent space induced by theta n?
Because it's the usual gradient, it's not.
And so and we're using Riemannian gradient, which belongs to this tangent space.
Yeah.
Good.
Okay, now let's take a look at the second equation. It's basically the same thing that we talked about, that we can just add some orthogonal matrix and some even tangent vector to get orthogonal matrix every time. And you can ask, why can't we just project this sum to the manifold? The answer is that the scheme will not be reversible, because you cannot reverse the projection. And you will lose energy when you project, and so scheme will not be symplectic.
And why we need Riemannian gradient if it cannot improve our second step, which
We cannot improve our second step because there were no gradient at all in the second step.
oh, but there are that we are trying to keep in the tangent space, and why we are trying to keep it there if it does not help us.
It will help us.
Okay.
So the idea here is to move theta n in the direction of epsilon r, but not in the tangent space, but along some curve on the manifold. Okay. So let's take a look at the third equation. Here, it's quite okay. We have Rn plus 1, a Riemannian gradient at the same point, but Rn 1 plus 1/2 belongs to the different tangent space. It belongs to tangent space at the point theta Rn. That this addition doesn't make sense, and we wanted, so we want to transport Rn plus 1/2 to the new tangent space before we add the gradient. So we need to be able to transport tangent vector from one tangent space to another one. Okay. Also, there is one catch. In the usual HMC, we sampled some initial velocity from the standard normal, but here we should make sure that this initial velocity is a tangent vector. The solution is to just sample standard normal noise and project it onto the tangent space. And actually it gives the same result as if we sampled from the standard normal into the tangent space and then computed how does this vector look in the bigger space. Okay, so we fixed almost everything except that we don't know how to update theta and how to transport r. There are such operations in Riemannian geometry. One is called retraction. It takes the point x on the manifold, some tangent vector psi, and you sort of stand at the point x, look in the direction psi, and you go and you move forward, and you move along some curve, and where you will end, this is the point which retraction gives. The same thing holds for the vector transport. You can take some vector psi and move along it, and your tangent vector will also be transported to the new point. And we need to define somehow retraction and vector transport for orthogonal matrices.
I still didn't understand how it works.
How
This transportation.
it's what we want.
Yes.
It's we haven't defined it yet, because for every manifold you should choose it somehow.
Mm-hmm.
And now we will choose it for the orthogonal matrices. So we will need some definitions and properties of manifold. So we will define all of n by p is the manifold of orthogonal matrices. There is also a tangent space, and there is a projection to the tangent space of some vector u. Okay, so we will need Cayley transform. Cayley transform takes some skew-symmetric matrix. It's A equals to minus A transpose. And we define Cayley of A as such matrix. You can prove that this matrix is orthogonal for every A. And we can compute its inverse as Cayley of minus A.
What is skew-symmetric?
Skew-symmetric is like you transpose the matrix and it changes the sign.
In Russian, this is кососимметричная матрица.
Yes. So we said that we need some curve along which we will move. And there is a way to define this curve, for example, like this. It has the following interesting properties. So for any epsilon, y of epsilon lies on the manifold, and also y of epsilon is continuous. That's why it defines the curve. And y of 0 is the same point x that we stand in. And we can compute the direction in which it goes, like the beginning. And it's the derivative by epsilon, and the point epsilon is equals to 0. And it's equal to ax. And if we choose x in the right way, we will get some direction, like any direction we want. And if we choose a as this guy, then tangent vector will be the projection of some vector u onto the tangent space. For example, if we take u equals to minus gradient, we will get some locally minimizing curve because we will go into the direction of Riemannian gradient. Okay. So, for orthogonal matrices, we can define projection like we just did.
So matrix A is parameterized by matrix U.
And
Right.
X.
Oh, X is given. X is our current
Yeah,
point.
yeah,
And U can be arbitrary orthogonal matrix.
yeah.
Right?
So U is the tangent vector, X is orthogonal matrix. Okay, we've defined the retraction. It's enough for the optimization, for example. You can devise an analog of SGD. However, for sampling, for Hamiltonian Monte Carlo, you need to take one step further, and you need to define vector transport. It's quite intuitive why it's defined like this. So take orthogonal matrix X. It's n by p, for example, where p is less than n. This orthogonal matrix is a set of orthonormal vectors. And as they are orthonormal, they lie on the unit sphere because their length is 1. And they are somehow arranged on the unit sphere. And imagine that these points, they have velocities attached to them. And if you rotate these points, the velocities should also be rotated, and exactly by the same way, that is, by the same rotation matrix. And this matrix is orthogonal, that's why it's the rotation matrix. And that's why we define vector transport like this. Is it clear?
Can you explain geometric meaning of this transformation?
Yeah.
Okay, so you have rotated columns of X somehow, because this is the rotation matrix. Imagine that you have like X, columns of X are the points on the sphere. Imagine that you move these points slowly in the direction where their velocities point. The velocities are rotated in the same way. They are like perpendicular to the points, like to the vectors to the columns of X, but they are rotated in the same way. For example, if you move along the circle.
So I mean that the velocity is a Riemannian gradient, or not really, or it can be any velocity?
It can be any velocity.
Not necessarily.
Not necessarily, yeah. So imagine that you have circle and the point on this circle.
So basically it's moving along geodesic curve.
Yeah. Like, no, it's not really geodesic, but it's close. Geodesic is something complex. So this, if you have a radius vector from the center of the circle to the point on the circle, the velocity is normal to this radius vector, and as point moves along the circle, the velocity also rotates
By the same angle.
by the same angle. Yeah.
So vector transport allows us to convert our old velocities to the new velocities, right? Which are needed at the third step of leapfrog integration.
Yeah.
And rotation is something we need at the second step of leapfrog integration, right? When we need to do what? At the second step?
Transform state.
Like, so here, this step is here, yeah?
Yeah.
Here, we can use our new method for going along some vector. We can use retraction.
A retraction of what? Of theta n plus 1?
Theta n in the direction of epsilon r n plus half.
Aha. So we convert theta n and obtain theta n prime,
Yeah.
which is already in the new manifold. And in this manifold, we make a step towards r n plus 1 half.
Let me show you
Do you mean
next
tension space?
slide. It's more clear here. here. So first we update R by the Riemannian gradient. Then we can we need to update theta, and we use our retraction.
Is it hard to compute Riemannian gradient?
Now we just project. Here is the projection, and we just plug in the gradient here. It's not
Okay, so it happens to be a Riemannian gradient.
Yeah.
Is it always true? You just take the gradient and project on the tangent space, or
It's always true,
It's always true.
for any manifold. Yeah. So you compute theta n plus 1, and now you need to transport r n plus 1 half to the new tangent space, which is at that point theta n plus 1. Well, so you transport it, and then you can update it. Yeah, and you can iterate it for any number of steps.
I think here a good geometric interpretation would be very nice.
Yeah. Like, okay, you can, this is your theta n, and this is your theta n plus 1. And your psi is r, and here is new r.
This is not exactly so.
Okay. So what's important about this algorithm is that time complexity is not very big. It's only O of np squared per iteration.
And what is P?
Like you have n by p, theta is n by p into orthogonal matrices.
And the number of iteration.
No, it's per iteration. Complexity per
So
iteration.
like, is it you have n just in two places? It's just those are different n's.
Oh, no, it's different.
Okay.
Yeah, I'm sorry. So the theta is orthogonal matrix of size n, n rows by p columns. Okay, so this scheme is reversible, which can be seen by the fact that retraction is reversible and vector transport is reversible, and the rest is like a leapfrog.
Yeah, and this comes from the fact that those are rotations.
Sorry?
That those are defined by rotation.
Yes.
Rotation is reversible.
Can you please explain what matrix A means? Is it some constant like basis matrix?
This is this.
Oh, thank you. So, can you one more time explain what means which are these matrices? So what is U? What is Z?
U is the direction in which you want to go. X is the point in which you stay.
Is U a regular gradient or Riemannian gradient?
It's any tangent vector.
Any tangent vector?
Yeah.
And Z?
Z is like this, like we stand in the point X and we move along the vector U and we transport the vector Z. So we transport Z from Tx to Tr of xu.
Usually U and Z are equal.
Yeah.
Okay.
And how do you invert in the matrix?
Well, you can write Woodbury identity, and then this inverse will be computed in p to the third to the power of 3, and as n is bigger than p, then you get this time complexity.
Okay, thanks.
So in stochastic case, the
You
equations.
need to invert, you need to solve equations. You don't really need to invert. Or you need to actually invert.
No, I don't need, but
Z is a matrix.
yeah, it's right that I need to solve some linear equation. I don't need to invert it and then multiply by this matrix. But this is how formulas look.
Okay.
Theoretically, how we implement them in practice, it's quite a different thing. So in stochastic case, we change the equations in absolutely the same way. So where needed, where we need to update theta, we use retraction, we use vector transport to avoid adding vectors from different tangent spaces, and so on. And most importantly, this scheme is symplectic. It can be proven. It's quite hard and long proof, but this is true. And so this algorithm will not have big rejection rate. It will be quite reasonable, and so this method will be effective. So, efficient.
Can you explain what happens with your normal density when you project your normal distribution onto the orthogonal matrix manifold?
There is no whiteboard here. So basically, you have standard vector from standard normal distribution, and then you project it to the tangent space, and your covariance matrix depends on the basis of the tangent space. And if you take this basis and construct a linear combination of vectors from the basis with standard normal coefficients, actually you will get some random variable with the same distribution as if you projected.
So density can compute in the closed form?
Yes, but we don't need the density. We never use the density of R.
But we can build kind of normalizing flow from this.
Okay. So what is the question? We don't need the density, and we can sample easily.
So we don't use Metropolis castings correction.
No. Like for HMC, yes, but we don't. For sampling R, you just project tangent vector.
Because this symplectic property of being symplectic gives only approximate energy conservation. So it means that you're still in correction.
But to compute correction, we have to compute density in your manifold.
Yeah, you can use the same formula as for the conventional HMC because R is the tangent vector. So yeah, we can compute the density, and you can use the same Hamiltonian actually.
So does it mean that density in every point, projected density equals original density times some constant?
Yeah.
Oh, thank you.
Are you sure?
Well, it works.
Well, that's always true. So,
Before projection of something, I'm not sure that this is just the value.
It will
of the
still be
quantity.
proportional, like the log density will still be proportional to the norm of the tangent component of the noise.
So I feel like if the curvature of your manifold is constant, then it should be true.
Is it?
Sure. But okay, let us discuss it later afterwards.
Yeah, okay.
Is this scheme symplectic only for orthogonal matrices or for arbitrary manifolds?
No, like this retraction in vector transport is defined only for orthogonal matrices. For another manifold, you should define them in another way.
But would the proof still for symplecticity still hold, or would I need to prove it once again?
You'll need to prove it once again. I don't know at the moment how to prove for any manifold.
So basically you just, you in the proof you actually use how you define these operations, not just the fact that you have them defined.
It's quite hard to define some retraction and vector transport that will still make the scheme symplectic for any manifold.
So here we have it relying on the scalar transform.
Yeah,
So to conclude, not every manifold has reversible retraction and vector transfer, right?
But if you have them like that, then you are done. So you need to just say that you prove the general technique, but you rely on reversible operations.
Is retraction really invertible?
yes, it depends on the Kähler transform, and if you take not A but minus A, this rotation matrix will be like you will get the inverse of this matrix.
It is not true for any Riemannian manifold.
Yeah. So, any more questions? No. So, we can move to the results. At first, we've taken some distribution over matrices, something like a mixture of matrix quotients. But then we needed some orthogonal matrices. We've taken the QR factorization of matrix W, and so we sampled in the space of Q and R. We needed something to compare with, as a baseline we used a different parameterization, which is written here. And this parameterization is ambiguous. Like you can, for example, multiply V by some constant, and you'll get the same W. And it can make the performance of the sampler worse. And this is what we see in the results. Like we computed effective sample size for standard HMC in this parameterization. And we computed effective sample size for our sampler. And we can see that it's much bigger.
What is effective sample size?
Effective sample size is the formula is quite unintuitive, but basically it's you take the number of samples and you divide by autocorrelation time, and it means that like, you can think of it as how many samples you need to sample in order to get one independent sample from the previous samples.
So the higher the better?
The higher the better, yeah. And minimum and median is taken with respect to different coordinates.
Is it the number of samples you should make to get to an independent step? So a small number, no?
It's a number of independent samples per number of total samples.
Yeah.
And what was the number of total samples?
Total samples, I think it was several thousands.
No, but it really matters whether it was 2,000 or say 50,000.
It was like 10,000, I think.
Isn't it better to show these numbers per one sample
Maybe.
as some fractions?
And what about
So that's the complexity of retraction and regularization methods, because one sampler can run fast and have a lower effective sample size, but if we measure the time to get the constant effective sample, so what is per second information?
You're right, but to compute this ambiguous parameterization, you need to, like, complexity of computing this parameterization is the same as time complexity of our method parameterization. So we didn't compare them by running time because the time complexity, the asymptotics are the same, and so compared just the raw sample number.
If it runs like 10 times slower, then you don't get any advantage.
You're right, but
So
it doesn't run 10 times slower.
And do we here assume that like deep sampler works a lot worse than HMC?
Once
Did you
again?
compare with other sampling techniques like deep sampler?
No, we've compared only with HMC in this parameterization.
How do you define a given sample for orthogonal matrices?
Yeah.
Yeah, I just saw this mixture of 4 Gaussians and I thought like,
Okay. Then we looked at deep learning. So we've taken some networks and made all the weight matrices orthogonal. For example, for convolutional kernels, we first reshape the matrix, reshape the kernel. We get some matrix and we want it to be orthogonal. For fully connected layers, we take the matrix as is. And it's the same for low-rank networks. However, we parameterize low-rank matrices using SVD. So for orthogonal networks, we get quite good results. Learning sits faster with orthogonal weights. Due to additional regularization, we get better validation accuracy than same, like the equivalent network with non-orthogonal weights. And ensembling also works, which proves that our method works. We get slightly better accuracy.
Do you perform stochastic gradient Hamiltonian Monte Carlo?
Yeah.
And so as far as I remember, in stochastic gradients Hamiltonian Monte Carlo, you need a friction term to correct for the gradient error.
Yes.
How do you compute it here?
Well, as I said, you can just take the equation, look at all the terms in it, and for example, for R, you have friction. You can just, if you can add this friction to the R, you will do it. And this friction also is also used in update for theta, and you just retract along this vector updated by friction term.
What are the architectures here? Your question?
Sorry?
What are the architectures here?
Well, on NIST we've taken some multi-layer perceptron, nothing convolutional. On CFAR10 for non-orthogonal networks we tried something like VGG16, and here we get the same accuracy, almost the same accuracy for twice shorter network, something like VGG8.
and which accuracy does VGA standard network?
Sorry?
The performance of the standard VGA network is slow.
Well, there is no standard VGG8. There are only VGG11, 13, 16, and 19. However, like we've compared this accuracy with non-orthogonal VGG16.
Okay, not orthogonal VGA, like the same architecture that you have, but without restrictions on the weights.
Yeah, we've taken the same architecture like VGG8 with non-orthogonal weights, and it got even worse accuracy.
How much was that? Like 80?
No, it was like 90 maybe. Yes.
So this learning scheme is non-Bayesian methods of Bayesian.
Why is it not Bayesian?
So what is the setup of the prior?
Prior? Yeah. Yeah, I should have said it. So for orthogonal networks, for example, take orthogonal networks, orthogonal matrix, which is n by 1, for example. You can see that you can place a uniform prior. And it's the same for any orthogonal matrix. You can take the uniform prior and
In the space of orthogonal matrices.
yeah, yeah.
What is the
will be
purpose
proper
of
prior.
orthogonal priors?
Sorry?
What is the purpose of taking orthogonal prior? Or uniform prior?
We need to define some prior.
And we do not have any preferences. So for us, any orthogonal matrix is okay. So then it's quite reasonable to define uniform prior.
Mm-hmm. And you can't, for example, specify orthogonal orthogonal matrices because I think all of them, almost all of
you
them
actually can.
well,
Are these vanilla Arlen's or LSTM?
Where do you see
Like a
LSTM?
I just always assume that if you are talking about it.
No. We can like plug in orthogonal matrices anywhere.
So is it true that we can just do orthogonal gradient descent and preserve the constraints of orthogonality?
Yeah. So we do exactly that.
No, but you do either that or you perform Hamiltonian sampling. These are different messages.
You can turn off noise
Right.
and you will get an optimization of it.
Okay.
Then, when you get to the pretty reasonable accuracy, you can run Hamiltonian Monte Carlo.
So when you're training single networks, you optimize it using vanilla gradient descent using SVD.
No, we can use the same.
So you
Retraction.
use the same Riemannian gradient.
Mhm.
And this is what is shown in the one network column or not?
Where? What do you?
In this table there was ensemble and one network column.
Yeah.
So one network is the result of optimization of this Riemannian optimization.
Yeah.
Mhm. So this is some analog of MAP estimate
Mm-hmm.
versus ensembling.
Mm-hmm.
Good.
Okay. So for low-rank networks, we compared. So we can parameterize low-rank metrics using SVD, and usually low-rank, like to get low-rank layer, you stack two linear layers. You have a bottleneck. So we've compared these two approaches, and blue is SVD, red one is the bottleneck. And as you can see that the training goes faster, validation accuracy is better, and so on. And the reason for that is that first, that bottleneck parameterization is ambiguous, and the second reason is that here we have U and V, which are orthogonal, and we use Riemannian, some Riemannian optimization or sampling for them, and so we get better training. So, are there any questions?
How slow it is?
It's not very slow, because especially if you take rank, if you take really low rank, then the rank is squared, but it's not that much, and essentially you have almost all of them.
I'm going to give similar results on recurrent neural networks, where the orthogonal matrices seem to be much more useful.
Well,
And where you could
I
potentially
don't
get
have-
much more impressive improvement.
I don't have them now, but I hope we will get them soon.
Are they actually useful in LSTMs, for example? Because usually that was one of the ways to make vanilla recurrent element work without LSTM or GRU. But everybody uses LSTM or GRU, so it's like
Well, it's not actually.
it's not
that
doesn't matter that much. There is already some protection from like gradients.
Agree.
Is it just one run, or you can average of
It's average.
And what about standard deviations?
Um,
Because for me, the
it's
difference
not
is
that much.
marginal.
Well, it's
And also curves are not that smooth. It shows that the sample of samples was not that big.
Yeah.
you're right.
Maybe 2 or 3.
Or maybe the learning process is too nosy.
Maybe.
But it's strange if it's nosy for some particular iteration. It's very strange.
Okay,
You should do more averaging somewhere.
I do. So to conclude this talk, we proposed an MCMC algorithm which can work with orthogonal matrices, which can be used to sample some other kinds of variables which are reparameterized using orthogonal matrices. It has better sample efficiency than this ambiguous parameterization. And I like that this method is applicable not only to neural networks, deep learning, and so on, but for any probabilistic models with orthogonal matrices. And finally, we hope that this method can be generalized to other manifolds, and this is our future goal. So, thank you.
Could you give a hint which manifolds they're talking about?
The most interesting is the manifold of tensors in tensor chain form.
Also, during your computations, due to numerical errors, it is possible that your weight matrix will stop being orthogonal for some point. Do you use some kind of numerical corrections to
Yes, you're right. Due to numerical problems, this matrix can be non-orthogonal. However, in practice, it happens only if you have a very big number of iterations, and even if you have this big number of iterations, we can from time to time project your matrix to the orthogonal manifold.
So you don't use these projections after each step. You just
No.
keep it as it is.
Yeah.
One question, have you used any kinds of regularization during the training process? Other than these orthogonal matrices?
No, I didn't.
So no dropouts, no batch normalizations?
For convolutional networks, I used batch normalization.
At anywhere? Including orthogonal layers? Or
Yeah,
not?
included, yeah. We tried to remove batch normalization for orthogonal and non-orthogonal networks, and orthogonal behaved better. So
what exactly do you mean? The degradation was less significant,
yeah,
but it still was.
well, it was, but it wasn't that big.
Well, one of our strategic goals is to get rid of batch normalization.
Yeah.
Because this is ugly procedure.
Yeah.
We should either replace it with some more elegant procedure or just reject it at all.
Yeah. And
You can reject it.
Yes, but now we experience performance degradation.
the experience it's less for orthogonal matrices, but it's still better.
Okay, any more questions? If not, let us thank the speaker for very interesting talk. I highly recommend everybody who is unfamiliar with this Riemannian optimization to review it again during your free time. Because I think that this technique is quite elegant and quite important, and we could potentially benefit in our research and our other research as well.